All right, we're starting section 5.1, which is on areas and distances. And before we start, I just want to kind of reflect on where we are. There are two main parts of calculus. There's differential calculus and integral calculus. Differential calculus is what we've been doing so far. The things that it's concerned with are slope of a tangent line, derivatives, and rates of change. Integral calculus is it's kind of like doing a lot of the stuff from integral calculus, but do it in reverse. The topics for integral calculus are areas under a curve, antiderivatives, which are also called integrals, and also the idea of accumulation. Like when you've got something and you know the rate at which it's changing, you can figure out how much it's accumulated. For instance, if you had suppose you had a pump that was pumping water, and it was pumping it, the rate at which it pumped it over time was changing. You could use calculus to figure out how much water is accumulated over that time. So anyway, chapter 5 is going to begin our study of integral calculus. And I want to start off by talking about areas under a curve. So let's just start with this example here. I've got the function f of x equals 16 minus 1/4 x squared. I've got that graphed here. The axes have different scales, but that's the function we've got graphed here. And I want to approximate the area under the curve. So all of this between the x-axis and the curve. I want to approximate the area of this thing using 4 rectangles. You know, the idea is eventually to figure out the exact area under here. But we're going to start it off by doing an approximation, and we're going to make the approximation get better as we go on. It's analogous to when we first found the slope of a tangent line. We did it by finding the slope of a secant line and then move those points together. Well, we're going to do the same sort of thing here, starting with approximations. So here's what I'm going to do. We want to use 4 rectangles. So what I'm going to do is come in here and I'm going to split this into 4 pieces. Let me do that with 4 lines. Now this is going from 0 to 8. So 2, 4, 6. If I cut this up into 4 rectangles, I'm going to get this, this, and this. All right, so those are going to be the sides of all my rectangles. Now, it says use the left endpoints to draw the tops. What that means is for this rectangle here, you know, I could draw the top right here, or I could draw it here. I'm going to use this left endpoint to draw the top. And so that's going to be my first rectangle. For the next rectangle, I'm going to draw the top using the left endpoint. And again here. And then again here. So the idea here is that we'll calculate the areas of each of these rectangles and add them up. I wish this had a fill tool. But we're going to calculate the areas of these rectangles, add those up, and that's going to be our approximate area under the curve. Now you can already look at it and tell that this has some problems with it. By finding the areas of these rectangles, we're definitely going to get an overestimate of the area underneath because we've got a lot of space over here where we're counting the area that we shouldn't, like up here above the graph. But it'll work for a first approximation, so let's do it. Now each of these rectangles has a width of 2. And now to find the height of these rectangles, the heights are different. The height of this one is 16. Let's make a little chart here. So we've got rectangle, width, height, and area. We've got 4 rectangles. The width of each of them is 2. Now the heights, for the first one, this is going to be f of 1, or I'm sorry, it's f of 0, because we're using this. So f of 0, which is 16. The second one is going to be f of, to get this point, that's going to be f of 2. The next one, the height of this one is going to be f of 3. Or no, f of 4. And then this one is going to be f of 6. So what are these different numbers? F of 2 is going to be, let's see, 16 minus 1/4 of 4. So that's going to be 15. F of 4 is 16 minus 1/4 of 4 squared. So 16 minus 4 is 12. And f of 6 is 16 minus 1/4 of 6 squared. So that's 16 minus 9, which is 7. Yep. All right. So those are the widths and the heights. And then the area of each one of these is just going to be the height times the width. So these areas are going to be 32, 30, 24, and 14. So if we sum those up to get the grand total, we'll get, let's see, 30, 60, 70, 80, 90, plus 10 is 100. So we get an approximation here of the area under that curve as being 100. And as we said before, this is an overestimate because we're counting a lot of space that's not included. So let's do this again. What I want to do now is I want to do the same thing, but I want to use the right endpoints to draw the tops of the rectangles. So if I do that, I'm going to get this rectangle, this rectangle, this rectangle. And then I'm going to use the right endpoints to draw my tops. So I'm going to add up these 4 rectangles. This last one, I'm using the word rectangle a little loosely here because it winds up having a 0 area. But if we do the same thing here, if we make the same chart, the rectangle, the width, the height, and then the area, we got 4 rectangles. All of them still have a width of 2. Now the heights, this first rectangle here, rectangle 1, its height is given by this, which is f of 2. The next one has a height that's given by f of 4. Then this one, this rectangle here, has a height given by f of 6. And the last one has a height given by f of 8. Now I could compute those numbers again, but I just did all of them upstairs, in the previous example. So let's see, those numbers were, starting at 2, the numbers were 15, 12, and 7. So we have 15, 12, and 7. And f of 8 here is 0. So the area of these rectangles is going to be 30, 24, 14, and 0. So if I total that up, what do I get? 30, 40, 50, 60, 8. And so that's an estimate using these. And that, of course, is going to be an underestimate because if I shade this in, we're missing a lot of area. The error we get is because we didn't count we didn't count this and this and this and this. So this is an underestimate. So both of these are approximations, and neither one of them is particularly good. I mean, they're off by a good bit. One of these approximations got us 100, one got us 68. So what can we do to make this approximation better? Well, there's several things we could do. One of the first things is if we've done both of these, it might make sense to take the 100 and the 68 and just take their average. What would that be? 168 over 2 would be 84. So 84 would maybe be a decent estimate of it. But things we can do to improve things is we could use the midpoints to draw the tops of the rectangles. What that would mean is instead of drawing the top here or here, we could draw the top of this first rectangle across there. And the second one, we could draw its top across there. And if we did that on each one of these, we'd get a little bit of error because we count something we shouldn't, and a little bit of error where we don't count something we should. So that would kind of balance out, and it would make it work a little better. Some other ideas are instead of using a flat top, use a slant. So what I mean by that is do this for each one of these. And so that would actually get you something pretty close. That's called the trapezoidal rule because each one of these shapes, when you have something like that, is a trapezoid. Another thing you could do is you could work out a parabola that connects these 2 points, and then another parabola that connects these 2 points, and so on. That would actually get us the exact value in this one just because this one happens to be a parabola. But in general, it wouldn't give you the exact value, but it would give you a good example, or a good approximation. So instead of using a flat top, use a curve. That's called Simpson's rule. And the other thing, notice this one's in bold because this is the one we're really going to do, is use more rectangles. So the idea is, if instead of using 4 rectangles up here, if we used 8, that would have gotten us a good bit of extra area that we should have been counting. So that's going to be the main idea for using multiple rectangles. All right, I've also got some tips here for the calculations. One is to use a spreadsheet to do all the arithmetic, because doing this stuff up here, it can get long. Another one is to use my online Riemann sum calculator. And so I want to look at both of those, but I'm going to put those in the next video because this one's getting pretty long. So we'll stop this video here.